everyone, I'm Alessia, and as I'm sure you all know by now, this presentation is going to be focusing on fear. So I want to make sure that we're all on the same page about how fear is created, at least for the purposes of the study, and how, despite how we might feel about it or how we might think, fear can actually be reduced and in some cases erased. So, if fear is created when a stimulus is paired with an adversive effect or a bad outcome. What that means, so for example, let's say your fear is of bees. So the stimulus would be a bee, and then the adversive effect would be getting stung or hearing a story about someone getting stung. Sometimes it's one traumatic event that causes fear, and sometimes it's repeated exposure of the stimulus to the adversive effect together. And once that happens, your brain begins to correlate the stimulus with the bad outcome. And so the next time you encounter the stimulus, you begin to get that fear reaction just purely because you expect the bad outcome to happen, regardless of whether or not it happens. So that's how fear is created on a basic level and what you need to know going into the study. And I'm sure we've all heard the term or the phrase, face your fears or face your fears head on. And there's actually a scientific method called exposure therapy, which uses this phrase pretty much. So exposure therapy uses a type of learning called extinction learning to pretty much erase the way that the fear was created. So that whole fear creation method is called conditioning. So extinction learning kind of uses conditioning as well, but erases the correlation between the stimulus and the bad outcome and replaces the bad outcome with a neutral or a good one. So that the next time that you see that same stimulus, you now associate it with something neutral or something good. So that's how fear can be reduced, and in some cases exposure therapy can actually erase it entirely. Exposure therapy is one of the most effective and one of the most common ways of reducing or erasing fear for patients with anxiety, PTSD, or any other phobias. And there's scientific research to prove that. But the scientists in my paper wanted to study the specific mechanisms in the brain that's behind that transition from the fear to no longer being afraid. Which leads me into my paper called A Dopaminergic Switch for Fear to Safety Transitions. And dopaminergic just refers to dopamine, and we're going to get into that later. What the scientists knew going into their experiments, they know the parts of the brain that are responsible for fear processing. Mainly, the study focuses on two, and then there's a third one that comes in later. So the first one is the ventromedial prefrontal cortex, which deals with, or VMPFC for short, which deals with risk, decision-making, and in particular, learning from mistakes. And you can see how that's involved with fear, because if you have a fear, that's going to affect how you act the next time you encounter that stimulus, so that would be decision-making. And another area of the brain that they know is responsible for fear is the amygdala, which deals with memory, decision-making, and emotional responses, which translates to fear because we're all familiar with the fight or flight response, so that has to do with your emotions, and the amygdala is responsible for that fear response. Again, they know those parts of the brain are responsible for fear, but the scientists wanted to know, first of all, how does the brain know that an expected event doesn't actually happen? How does it process it? And again, as I said, what is the specific mechanism in the brain that's dealing with that transition from fear to safety? The system that they wanted to look into was dopamine. Dopamine is a neurotransmitter, and for the purposes of this study, you should think of it as a messenger that sends signals to other parts of your brain and your body that's responsible for the feelings of wanting and liking. Dopamine tends to get the reputation as the neurotransmitter responsible for feeling good, but that's kind of an incomplete picture because, yes, dopamine does deal with, when you're happy, dopamine is fired, and sometimes when you feel good, dopamine does get released, but there's evidence that shows that any important event at all, so something that's surprising or shocking or major, will fire dopamine. And in that case, it would have to do with fear. So let's say you're in a car crash or you get surprised. There's evidence that shows that dopamine is fired during that experience as well. And dopamine deals with reward or relief, which a lot of times will translate to the feeling that you get when you have fear, but nothing bad actually happens. That's often felt as relief, and that's why they also wanted to look at dopamine. And again, sometimes it's just fired when you get a general feeling like being happy. The scientists wanted to find a specific region in the brain to study because of the method they were using that I'm going to talk about later. And their candidate circuit, so that region that they're looking at, was the VTA dopamine system, or the ventral tegmental area dopamine system. This is the origin of many dopamine pathways in your brain, specifically those other parts of the brain that I talked about before, so the prefrontal cortex and the amygdala, and then I'll talk about the nucleus accumbens later. They know the VTA region is responsible for reward and relief, and this region has a known connection to fear, but again, they want to know like the specific mechanisms. They want to know where in the fear creation and fear extinction process does dopamine play a role, and they also want to know, is it a cause or effect? So is it when you're afraid dopamine gets fired, or dopamine gets fired and therefore you're afraid? Okay. The scientists use a method called circuit-specific optogenic inhibition, which is a mouthful, but I'm going to go over it step by step. The circuit they're referring to is the VTA dopamine system. Again, that's the origin of the majority of the dopamine pathways in your brain. Circuit-specific means that they were only targeting that area with their research. Optogenic, I'm going to have a whole slide on it next, but it's, in short, using light to inhibit dopamine. So that's how they're going to see if it actually plays a role in fear. And inhibition just means blocking dopamine from being released. So in short, they're using a light system to block the dopamine in the VTA region to see if dopamine plays a role, where it does along the fear creation and extinction process, and how much of a role does it actually play. So optogenetics. This is super cool. It's a little complicated, so stick with me. The first part of optogenetics is pairing two genes together. The first one that they're using is the enhanced yellow fluorescent protein, or EYFP for short. And then they're pairing, well, some control mice just have that protein, so just think of those as control mice. And then the mice that they're actually going to be blocking dopamine with, they're using a protein called halorhodopsin, which all you need to know is that halorhodopsin is activated by light, and when halorhodopsin is activated, it blocks dopamine. So they're pairing those two genes together. They're injecting them into an AAV virus. They're injecting that virus into the specific part of the brain. In this case, it's the VTA dopamine region. From there, they're inserting what's called an optrode. It's basically a little light in the mouse's brain, specifically in the VTA region. And then the big picture, when the light is on, halorhodopsin is activated, and therefore dopamine is blocked. So think light on, dopamine blocked. Are there any questions about that? Okay. So the first experiment they did, they had to create the fear in the first place, and then they wanted to test where in the extinction process dopamine plays a role. First, they're going to play 20 short beeps for the mice, and then they're going to give them a little shock in their cage. So that's the fear creation and the conditioning, so that the mice associate the beeps with an adverse effect. Next, during the fear extinction phase, they're going to play those 20 beeps, but there's no aversive outcome. So they're going to see how much the mice freeze up and therefore are afraid, and how much that will hopefully reduce over time. There's three groups of mice that they're studying. One is the control mice. Those don't have the halorhodopsin, but basically just think of them that no dopamine is blocked at all. So that's just the control group. Another group is having the light turned on and therefore dopamine blocked during the conditioned stimulus, so when they hear the 20 beeps. And then a third group of mice is getting dopamine blocked during the expected adverse effect period, so when they are expecting to get shocked. And then lastly, there's a retrieval phase, which is pretty much a final measure of how much these mice are afraid, and it's a comparison between the groups. And again, that's only showing that's only playing the 20 beeps, and there's no shock. Oh, sorry. So the first thing I want to look at is the group of mice that had their dopamine blocked during the conditioned stimulus or during the beeps. And we're comparing, so that's the orange line, and compared to just a regular group of control mice. So here, this is the training section. You can see the first one, there's no fear because they don't know what's about to happen, so they're not expecting anything bad. And then almost immediately in those next two training sessions, the fear is beginning to be shown. And they're measuring freezing levels, which indicates fear. And then you can see in the extinction phase, when the freezing levels are going down and therefore the fear is going down, there's actually no significant difference between the inhibitory group and the control group, which just means that as far as they can tell from this study, dopamine does not play a major role in the fear extinction process, specifically during the beep or the conditioned stimulus phase. However, this next group is comparing the group of mice that had dopamine blocked during the expected shock period, so the time after the beeps, and comparing those mice to the control mice. And you can see around day 5 or 6 of extinction, there starts to become a significant difference between the group of mice that had dopamine blocked and the group of mice that didn't. Which indicate, and you can see that that change is really major in the retrieval phase, so that's that final measure. This indicated to the scientist that dopamine does in fact play a major role in the expected adverse effect part of fear extinction learning. So while it doesn't play a role in the conditioned stimulus part, it does during the expected shock. So that's what they know so far. So that experiment was based on extinction learning, but they wanted to ask, what about fear creation? So what about that training period? Does dopamine play a role then? And if you think back to what I said earlier about dopamine, anytime a major event happens, there's evidence that shows that dopamine is fired. So they're thinking anytime when the mice originally get shocked, dopamine is fired, and therefore dopamine will play a role. So they wanted to research into that. The second experiment they did, similar to the first, they played 20 beeps and then a shock. And there's 4 groups of mice. The first one is the control that never have dopamine blocked. The second group of mice has dopamine blocked during the 20 beeps, the first time they hear it, so when the first time the fear is being created. The second group of mice has dopamine blocked during the first time they get shocked. And then the third group of mice is pretty much another control. It's called the offset group. Just think of it, they get the dopamine blocked at a part completely after the 20 beeps and the shock, so just think of that group as another control. And then they're doing the retrieval, which is the final measure, and there's no beep played, there's no shock. They just want to measure fear levels. The scientists' hypothesis was that inhibiting dopamine will mean less freezing. So they predicted that dopamine would be fired during the shock, and therefore make a stronger fear memory. So if they're inhibiting dopamine, the fear will be weaker. So inhibiting dopamine means less freezing and less fear response. So on the left in the C graph, that's a group of mice that had dopamine blocked during the beeps, and they're comparing, the orange is the group of mice that actually had dopamine blocked, and the gray is the control group. What you can see is that there's no significant difference, which just indicates that dopamine doesn't play a major role the first time they encounter the conditioned stimulus. However, look at figure B. There is a significant difference between the group of mice that had dopamine blocked and those 2 control groups, which means that dopamine does play a role in the adverse effect the first time they see it, so when they're creating fear. However, if you think back to what I said, their prediction was that fear would actually be lower, and what they see is that when they inhibit dopamine, fear is actually higher. So that is the complete opposite of what they predicted, which is interesting because it shows that A, dopamine is way more complicated than we thought, just as it's more complicated than the feel-good hormone, it's more complicated than any major event at all will activate dopamine. And if it is activated, maybe it plays a role in reducing fear instead of what they thought it would be increasing fear. So that's something they definitely want to do further follow-up studies on. The final experiments, which we don't really have time to go over the process because it was a little different than the first one, but you can think of it similarly, where they were looking at projection areas. Remember I talked about VTA dopamine, that's what the region of the brain they were studying in the first 2 experiments. Now they're looking at those areas that branch off from VTA, and they're still receiving the dopamine signals, but it's a little more specific. So they, as was indicated from the past experiment, dopamine is way more complicated than just putting a blanket statement on saying dopamine helps fear, dopamine doesn't. So they want to look at the specific parts of the brain that deal with fear and see dopamine's relation to that. So they looked at 3 areas, the nucleus accumbens, the VMPFC, which I talked about earlier, and the amygdala, which I also talked about earlier. What they saw when they inhibited, and this is pretty much the first experiment, it's a little different process, but they're inhibiting dopamine during the extinction learning, and specifically during the expected adverse effect. In the nucleus accumbens area, when dopamine was inhibited, those mice experienced more fear than their control mice. On the flip side, and the nucleus accumbens is the area that deals with rewards in your brain. On the flip side, the ventromedial prefrontal cortex area, which deals with risk and decision making, when dopamine was inhibited there, that group of mice had less fear than the control mice. And then their last experiment, when they inhibited dopamine in the amygdala region, which deals with memory and emotions, that fight or flight response, there was no difference between the 2 groups, which again just proves that you can't say dopamine helps fear or dopamine doesn't help fear, because it really depends on the region of the brain that you're looking at. And those, as I said at the beginning of the presentation, those areas of the brain deal specifically with different aspects of fear, and dopamine plays different roles in those areas as well. So just to recap, in the first experiment, they found that dopamine pathways are active during the expected adverse effect periods when they think the shock is going to occur. In the second experiment, they showed that and that's the extinction learning part. In the second experiment, they showed that dopamine pathways are active specifically during the adverse effect itself, when the fear is first getting created. But it's not in the way that they predicted, so they need to do follow-up studies on that. And then the final experiments, again, those are the 3 different areas, all have different responses to inhibiting dopamine. Just goes to show that you can't just make a prediction, or you can't just inhibit dopamine and expect fear to increase or decrease. You would have to specifically target those regions and target them during a specific part of the fear creation and extinction process to actually make a difference. So this experiment is really important if we're going to be potentially manipulating dopamine, because you have to know when in the process you're going to do that, where you're going to do it, and in what way. So obviously they need further research, because just from those 3 experiments, they showed that their predictions were in a lot of cases wrong, and it's way more complicated than we thought. Does anyone have any questions about this? And I have a final thing to think about. Okay. I just want to leave you with this note. The future of exposure therapy, that's the process that uses extinction learning to override your fear. The direction it's going in is using virtual reality and computer imaging, which makes sense because it's an easy way to make a safe and controlled environment to expose a patient to their fear in, and that's how exposure therapy works. But what do we know about computer imaging, video games, and virtual reality is that it uses your dopamine systems in a completely different way than if you're processing regular reality instead of virtual reality. So this experiment is really important because it's imperative that we know how dopamine works in regular fear creation and fear extinction before we start using computers and virtual reality, because exposure therapy is long-lasting and has severe consequences. It could be used in a positive way or in a negative way. And they're assuming that using virtual reality is beneficial and improves the exposure therapy process, but it's important that we actually study what it's doing in your brain to make sure that it's actually improving exposure therapy. Okay, thank you. If anyone has any questions. Okay, thank you. And next week we have Nabil presenting. Okay, next week Nabil has a really cool study that suggests that birds can actually sleep mid-flight. Correct? And it's really cool, so come next Friday CP.